let's do. Actually, now things will be easier. So now we will be looking at the inversive group. Inversive. So what is the inversive group? This is the group that is, and that's important. It's a group generated by the inversions. So this is the group which is generated by this inversions. Meaning that if you take all possible compositions and so on, right? Yeah. So for every inversive line, for every circle or every circle, just for every inversive line, you have this inversion, which is a function, it's a bijection. And so you can, and so these have all inverses are there. But then you can compose and generate a group, big group, right? And that group is called the inverse. That group is called the inverse group. But you notice that this group is being generated by elements of order 2, because gamma c as elements of this group have order 2. Gamma c as functions have order 2. Okay? So that I will say as M is a Coxeter group. In fact, Coxeter group is named also after him, after HSM Coxeter. Group. You can look at the definition of, basically I'm talking about any group that is generated by elements of order 2, that can be generated by elements of order 2. And these are very interesting. Okay? You should look at this online at least. And there are books, but you can look at it online a little bit for the moment. And this is true that if you look at the isometry group, and I'll just define it. This is another group for which group actions are useful, but in a simple way, so I'm not discussing it. Isometry group of P2. And what is, I mean, of this is R2. R2. What is this? This is basically just the collection of all functions, very intimately connected with linear algebra. The stabilizer of the origin is actually the GLN, or it's not GLN, SLN. Sorry, ON. Orthogonal group, orthogonal matrices. Okay. But it's to begin with, it's just functions from R2 to R2 such that it preserves distances. Right? So if you look at fx minus fy and look at the distance, and that is isometry, iso of the metric. Metric space is a metric space, so it's isometric in that. You're taking, and these are obviously bijective and so on and so on. And that group is iso, and it's contained in this. That you have to understand the classification of this. This is given in the first chapter of this book, or you can even read the standard Artin's book, Artin Symmetries. Artin's book, Artin Algebra, standard algebra book, abstract algebra book, Artin. From in there is a book on symmetry, which is not so abstract. It's probably the most non-abstract chapter in the book, and it's in this book they prove that. So what they prove is that all the isometries can be generated by reflections. Any isometry of the plane, usual plane, you can get by reflecting about lines and compositions. Any function can be written as a composition of reflection. Wonderful fact. Wonderful fact. But, and of course, this has all the reflections about lines. This even has more. Okay? So this is true. And this is it. And it actually, I think, might be wrong. I think it's a normal subgroup, but I think it's a normal. But let me not get into that. So that's the goal of the discussion. What we are going to consider is in a similar flavor to that theory, but look at this. We are going to look at this subgroup. This is actually normal This should be normal, I suppose. If I'm wrong, correct me. M plus. What is M plus? I should define it. M plus is a subgroup. Before defining M plus, give you some motivation. Otherwise, it sounds a bit strange. Yeah. Yeah. You look at this circle, let's say, or in fact, just take a line, and take these two lines. Okay. L1 and L2. Okay. Right. Now, this is the reflector line about which we are going to reflect. Okay. If you reflect this line, and now focus on this angle. I want to talk about something like orientation preserving and orientation reverse concept. That's sort of comes out. It's not a mandatory, it comes out. So look at this orientation like this, theta. Now, if you reflect this, then what happens? It's clear that L1 becomes deflections. You people are very comfortable with. Right? Orientation is the only this inversion was the only thing which I have not seen earlier. So not a problem. You see, I mean, this is how mathematics is. You have to see other kinds of things. When you do Riemannian geometry, you have to see that those kind of motions, the hyperbolic, some other kind of. Hey, you have to keep yourself open to learning this. So it goes and it goes here, and this line goes here. Right? And of course, you can prove using some simple congruency and so on that this angle also is theta. Right? But the orientation reverses. The orientation reverses. Why am I? In what sense am I saying? I'm saying that if you look at this arc, that will actually. Yes, right. This arc, if you travel along like this, if you dot some points, and you dot the points in the image, you will see it will go in this direction. And these are different orientations, right? This is anti-clockwise, that is whatever. This is anti-clockwise, this is clockwise. So these reflections are preserving angles, but they are reversing the orientation of the angles. They are preserving the magnitude of the angles, but they are reversing the orientation of the angles. Okay, and these are probably, again, one can go into a whole talk about all these things, but not saying it. But very important concept. Very, 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 very important. You cannot like this very important. So, but every very I have some in my mind. I have some name of some topic. But let me not get into this is okay. Orientation reverse. But if you take this reflection and you take some other reflection and you compose them, theta will go to theta again. If you apply then those two lines, image lines, you apply again you will get theta, and this time the orientation is going to get preserved. Correct? Yeah. And so that's why composing two reflections gives you a orientation preserving function, which preserves the orientation between the lines, but also preserves the angle between the lines because both the things preserve, right? But orientation is preserved because you're doing it twice. Okay. Same thing applies to inversions also, but you may not be able to see it directly. Okay, this is a very fantastic fact that if you take this circle and you take any curve, any two curves, take some angle, you can define it using tangents and so on. And you reflect, if you do apply this will go to some other thing. Now it will not go to circle or something, but this angle will remain the same. That's the magnificent fact. It's there in the book. Easy to prove, but this is kind of fact that you should love as mathematicians. So locally, it's like this, nothing changes. What more do you want? Such a bad function, but locally nothing changes. If you want to call it bad in some sense, locally it doesn't change. But orientation changes. that is why we want to consider M plus, which is orientation preserving, and that's the motivation for this. C1 and C2 are, so this is generated. This is not set. This is generated from these things. Okay. This was generated by everything, and this is generated by only those things which are compositions of two inversions. Okay. And that's why we call it plus and so on. And SON, the orthogonal group and the determinant one subgroup, SON is related with this. Will not be. And the statement of the day, the statement which we want to prove, I think we will not be able to do it today. But a lot of interesting groups and subgroups have arrived, but this is okay. M plus. So should we go for 10 more minutes? Is that okay? Then we'll stop.
Okay, sir.
Okay. And if you want me to stop now, I can also do that. Okay. I mean, probably maybe if you have something else, that's it.
So हम एक बात बोलूं?
Yeah.
मुझे ना बहुत less interesting subject लग रहा है.
Okay. So what should you do?
ना मतलब group action करना था, ये सब कर रहे थे. मतलब interest नहीं आ रहा इसमें.
Right. Right. Anyways, I mean, but right. Then we take some other examples of group, but nonetheless, I mean, I will prove that this is simple. If I don't prove that it is simple, then okay, then maybe we'll see that. Yeah. But anyways, let me then tell you what I want to tell. Then that's why then you have to choose a topic of group action. Anyway, so okay, maybe it's possible. Yeah. Okay. Okay. So
next year we can do silo.
yes, yeah. Silo, if you want to do that, also fine. Yeah. I mean, this is the group action that I know. Okay. Silo is also fine. And that's a standard topic. But yeah, so I mean, you told me to choose something, so it's okay. Anyways,
I thought okay.
Yeah, that is what happens. Yeah. Okay, no problem. I mean, it's yeah. So okay. Anyways, yeah. So then the claim is that for example, example. Right? So you see like one of the gamma knots. So basically, we want to know because you want to prove that M plus is orientation preserving. Sorry, because you want to prove M plus is simple. Right? That's what you want to do. You want to prove that M plus is simple, right? So for that, you have to understand how the elements of M plus look like, right? And actually, they look very simple. That's very easy to prove. So, and the claim is that elements of M plus look like these are called Mobius transformations in the theory. Boom. These are like the simplest things on earth. Right? I mean, this is so simple compared to 1 by z bar. And why is this happening is not surprising, right? Because it is something like, I mean, look, if you consider because you're composing twice, right? So if you take z going to 1 by z bar as one of the functions, and then you take another thing from that M, for example, what would you take? I mean, you can take some conjugate of it, right? So inversion about any circle will be some conjugate, right? And I mean, in the end of the day, it just happens to be some coordinate shift and so on. So maybe you can take this function. No, this is a reflection about the x-axis. Yeah. and then we want to compose these two functions. That's how that thing will look like. Correct. That's how that thing will look like. So if you take this as your gamma c and this as your gamma l, then if you compose them, then how does it look like? It is just 1 by z. And this fits in this, right? So this is the thing. This is what I'm talking about. This thing is in C4. I mean, I'm just saying these are complex numbers. Okay, right? And that's all I'm talking about. That every function, everything here will look like this. Okay. Again, it is not difficult to prove that. All right. So this is just a small explanation of that. Okay. But as I said, like that's why we proved that thing, right? That any inversion is sort of a conjugate of the inversion around the origin, right? And that fact you can use to prove that because the basic inversion looks like this, any inversion will look something like this with a conjugate, yeah, some az bar plus cz by bz bar plus b, something. But then because you're taking composition of two such things, the bar will go away, roughly speaking. Okay? So it will look like this. Okay, but I'm obviously this is not a proof of anything. It's just okay. Now, so this was number one, and number two, you can notice that this thing I can write as a matrix. I can write this as a matrix, correct? I can write this as a matrix. And this matrix is basically, I mean, obviously you see that if you have a function, so now you see basically this thing az plus c by bz plus d is a bijection, right? If it is a bijection, then what condition should you have on ABC? Right? It should not be constant, right? When can it become constant? It can become constant if AD minus BC is equal to 0. All right? Just check it. Just check it. It's a simple check, right? It's a ratio of ratio, and you can check it becomes constant. So you don't want that, and so you put. And this actually corresponds to the fact that this is GL and R, invertible matrix. I see. Correct? Yes. So basically, every element of M plus gives you a matrix GL and R. This is a rough picture. But then, let me check. Okay, so basically every function which is like that, every element of M plus gives you a matrix. This is now I'm going in a very rough way. Every element of M plus gives you this matrix, which is GL and R. But then you have to ask, when do two functions give me, or when do two matrices give me the same function? That's possible, right? I mean, if I take this matrix and I say 2 times this, I take this function, the function doesn't change, but the matrix changes. Got it, right? Function doesn't change, but the matrix is changing. So that is why you see many matrices will correspond to the same function, and that is why we have to consider GL and R modulo. Yeah, this. Yeah. I mean, how do you get SL and R then? I don't know the center. Right, they are doing it more direct. Anyways, yeah. So let me not get into this. There are some things involved. Okay? So the point of this is that finally you get, I mean, this GL2. Okay? Finally you get SL to R. Not finally, you get SL to R, and then you can see that when you can see that identity and minus identity also give you the same function. And so finally, that's how you get the PSL to R. And I have not defined PSL to R. I defined it, but maybe I'm not. And yeah, then actually there's a there is some story after that also. So I can suggest that if you are interested, for Vaishnavi, for example, if you are interested in this, I suggest you can read this. Okay, you should read this, and
Okay.
you can. I mean, see, if you think that this is the thing to do at the moment, okay, otherwise you should not. Okay, because there are some other things, and basically it's a very nice all the group theory, solvable groups and everything which you have learned at some point or other comes in this picture. And this chapter, and you can see this is very accessible. You don't get more accessible, non-trivial group theory from here. Trivial group theory you will find in there, but mixing it with geometry and so on, it comes in a very simple way from this chapter in particular. Okay, so you can read this at the moment, and if you want, don't if, like you can also read this in the future. But this is one of the topics that you can keep in mind. Yeah, yeah. So sorry, I mean I couldn't get to the matter actually. That's the problem because I initially have to. So maybe we'll not, as Arnab was also suggesting, we should not consider this, continue with this the next day, because probably it's, I don't know, bad topic. It's not bad to me, but yeah. So that's all. Okay, and that's it, and we'll continue. So usually we also have this class on Tuesdays 8:30 p.m. where maybe we'll do silo subgroups next day. I will be doing that, and if you want to just attend by, you can just come and see. And yeah, this is the story. And we stopped. I think we went for very long today. What to do? I wanted to share this. Okay, then let's stop. We'll meet at our respective times. If you have any questions, please tell me. I mean, if you have any to ask any.
Not today.
Oh, all right. So then, all right. Then we'll meet at our respective.
Tuesday 8:30.
Tuesday 8:30, right? So Tuesday 8:30 we'll meet, and we will do something along the lines of silo subgroups.
I will send you some questions about that. So
Okay, so
maybe
you
you
send me the
can
questions,
focus.
then we can try those questions and see if we can solve them. Okay, and yeah, and also Tuesday we are meeting. I think Vaishnavi, and we are to meeting on Tuesday. We'll discuss some things from real analysis. So if I don't know if it's possible for you to come, you can.
Okay,
Okay,
sir.
so that's the combined. All right, bye then. Take care.